All right, so we started section 14.2 last time, right? And I think that we had gotten through our example that were even and odd numbers pulled out of a hat, but we hadn't done the spinner one. Is that true? Excellent. Okay, so we're going to go on to the spinner question. Looks like this, example 3. It says, suppose an experiment consists of spinning the first spinner followed by the second spinner. So on part A, we're going to list the sample space. So Kylie, this is kind of like the one you asked before, but with a multi-stage experiment. So for a sample space, for this, we're looking at curly braces because we are looking at a set. Okay, so we're going to do our curly braces. I want to make that thicker now that I'm back in my slides here. Okay, so we have our curly braces. And we're going to list all the possible spins that we can do. For example, I could spin the first one time, and then, or I could, not one time, but land on the number 1. And then on the second spinner, I could spin that one. I could also land on the number 1. So a really nice way to organize that is like an ordered pair. It's not the only way. You could literally just write down 1, 1, and it looked like the number 11, and that would be okay. But separating them out maybe gives us a little more distinction that we're not talking about the number 11, okay? But I don't have to roll or spin, rather, the 1 and then the 1. I could spin a 1 and a 2, right? Or I could spin a 1 and a 3. So those are all the ways that I could spin the number 1 on the first spinner with anything that happens on the second spinner. But I could also do the number 2 on the first spinner and match that up with the number 1 on the second. Or the number 2 on the first spinner with the number 2 on the second. Or the 2 on the first spinner with the 3 on the second. So there are 6 outcomes that can happen when I spin this, and that should sort of make sense because there are 2 options here and there are 3 options here, and 2 times 3 is 6. Make sense? I'm gonna have 6 different things in my sample space. Now in this particular sample space, all of these are equally likely. Can you see why? It's because of the way the spinners are designed, right? The first spinner is 50-50, it's split evenly in half. And the second spinner, if it's drawn well, and I think it is, it's split evenly into thirds. So each of these probabilities is equally likely. You could have spinners where that doesn't happen, right? So use some common sense with how we're going to moving forward from this. I don't have to have a tree diagram for this. And the reason I don't is because of the way that these are equally likely to occur. Now, could I draw one? Of course you could draw a tree diagram. If you wanted to, absolutely you could. If you wanted to do that, it would look something like this. You'd have either a 1 or a 2, and then off of it again, you'd have 3 branches here and 3 branches here, and they'd be all the 3 numbers from the second spinner. 1, 2, 3, 1, 2, 3, like this. This would be 1/2 and 1/2, and all of these would be 1/3. But notice what's happening along each of the branches is if you multiply along every single branch, you get 1/2 times 1/3, which is 1/6, which is the same thing that happens down here. If you count them, each one of them, there are 1 out of 6 options. Okay? So this is one of those cases where if I wrote my sample space out, I wouldn't necessarily have to do a tree diagram. We're taking a look, though, at the probabilities. So we're looking at the probability of spinning 2 even numbers. So looking at our sample space below, or looking at your tree diagram above if you prefer, where do you see, or what do you see as the option for spinning, option or options for spinning 2 even numbers?
Spinning 2 and then 2 again?
Yep, it's just this one, right? It's the only way I can do 2 even numbers. Now notice if they said 2 odd, I'd have lots of ways, right? Okay, so the context matters here. I would have more options. Would I have more options? Yeah, I would have the 1, 1, the 1, 3. I'd at least have 2 of them. I'd have more than 1, okay? So there's 1 here. So the probability is 1 out of how many options? 6, exactly. If you were doing it from your tree diagram, you'd be looking along the branch that says 2, 2, which is right here, and you'd be multiplying them, and you'd get 1/6. Make sense? Great. How about spinning at least 1, 2? So I'm not gonna keep going back to my tree diagram at this point, but you can if you wish. I'm gonna look at my sample space because it's sufficient. Down here in my sample space, if I want to spin at least 1, 2, it will include the one I already did. At least one means 1 or more, That one has more, but that's fine. So what others have at least one? So we've got 1, 2 here, and 2, 1 here, and 2, 3 here, right? All of those have at least 1, 2. How many of them are there? There are 4. Out of how many again? 6. So this is 4 out of 6, but as in every case, we're going to simplify fractions to their simplest form or their most reduced form. And so we'll divide by 2 on the top and bottom, and we'll get 2/3. So the probability of spending at least 1, 2 is 2/3. Okay, exactly. What does exactly mean that this phrase up here at least doesn't mean in terms of this context? I can't have 2 2s. So in this scenario where I've underlined everything, I'm going to remove that one. I say I am, but it's not wanting to go away. Let's try it again. How about like that? Each of those have exactly 1, 2 in them. How many of them are there? There's 3. Out of how many total? 6, and that reduces to 1/2. Fantastic. Okay, make sense? All right, so this problem is dreadfully old, but I think if I changed son to daughter, it would still be accurate. When I purchase a new shirt for my son, there is a 0.15 probability that he will stain it the first time he wears the shirt. If the shirt is stained, there's a 0.2 probability that I will not be able to adequately remove the stain. In other words, it's stained permanently, okay? What is the probability that my son's new shirt will be permanently stained the first time he wears it? Okay, do you understand the context? So I'm specifically doing this example not because it's my son and shirts and clean, but because I want you to see that trees don't necessarily have to have even or exactly the same number of branches coming out of every category. Okay, so this one had, it split into 2 and then they all had 3s, right? This one's not going to have that. So what's happening on this one is the first time he wears it, one of 2 things happens. What are those 2 options? Yep, he stains it or there's no stain. So I want you to think practically speaking, what am I going to have to do if there's a stain? Like if I want it to go away, I'm going to have to wash it in some way, treat it actually, right? Like I'm probably going to have to treat it with something and make sure it comes out. But what if it has no stain? I don't have to do anything special to it, right? There's no additional steps required. It just goes in the hamper. It can be washed whenever it's washed. So on this one, the only additional set of branches are actually going to come off of the stained category because the no stain doesn't require any special treatment. Now, what are the 2 options when I try and get the stain out? Yep, the stain either comes out or it doesn't. This is the permanent category. Okay, so we do not have to have 2 branches extending from the no stain because there's no branches necessary. Y'all good with that? The other thing that's unique about this one compared to the other things we've done is they have unequal probabilities. Okay, we had that happen with our people going to Hawaii a little bit too, but when we did it with that one, we did it with fractions. This one's got decimals, so it feels a little bit different. So it says the first time he wears the shirt, there's a 0.5 probability that he stains it. So we're completing the tree diagram. That means I need a number on that bottom branch. What would it be? 0.85. Okay, how do you get 0.85? What'd you do to get that?
1 minus 0.15.
Right. So I mentioned it before, but let me remind you again. One set of tree branches has to add up to the number 1, right? So in order to find the 0.85, I would do 1 minus the 0.85. Y'all good with that? Or I'm sorry, 1 minus the 0.15 to get me to the 0.85. Said it wrong. Okay, fantastic. How about stain comes out? What's the likelihood if it stains it that I scrub it and it comes, well, actually, where does this number go? Let's do that. Where does the 0.2 go? It's got to go somewhere. It's the doesn't come out. So it's actually, I actually know the bottom one. I know how likely it is that it's permanently stained. It's something like, I don't know, blood will come out. Sharpie. Sharpie's not coming out. It's probably Sharpie, okay? I don't know. So then, what is the likelihood that it does come out? What's the probability on top?
0.8.
0.8. Okay, everybody good with the tree diagram? Okay. Now that we've got the tree diagram fully filled in, we're going to answer the question asked. What is the probability that it will be permanently stained? So this is the tree branch that it's describing. What do I need to do to find that probability? Close. Multiply. We're going to multiply along tree branches, okay? There are cases where we add something, but it's not along a branch, okay? We'll come back to the cases where we add something. But if we're going along a branch, right, from start to finish, it's always multiplication. So what is 0.15 times 0.2? Yeah. What is 1500ths times 2/10? 0.03 or 300ths. Okay, so if you're thinking in terms of percentages, you don't need to write that down, but what percentage chance is that? 3%. There's a 3% chance. It's not super high with the example given, but that's what this is looking like. Okay, does that make sense? Okay, let's do one that's more like a problem C kind of question. Joe says that if a family has 2 children, then the only possibilities are 2 boys, 2 girls, and 1 of each. Because there are 3 possibilities, the probability of having 2 boys is 1/3. Is Joe correct? Explain. So let's draw the tree diagram that represents this so that we can adequately answer, right? This is not the only way to do this, but it helps to get a picture of it, of what's going on here. So if a family has a child, there's 2 options. What are they? Boy, girl. Makes sense, right? And then whichever one they have in this scenario, where they're going to have a second one, it says. So again, second child. If I have a boy, I still have an option of a boy or a girl. If I have a girl, I have an option still of a boy or girl. Now we'll fill in the tree diagram's probabilities, but this right here is probably enough to answer the question. So let's actually pause on filling in the probabilities so you can see why I'm saying that. He contends that there's only 2 possibilities, 2 boys, 2 girls, or 1 of each. And in some ways, that is a true statement. Agreed? Right? This is the only options. Like this is really the only options. But what error is he making in saying that it's 1/3? Because I have 4 options here. Because there's the end of 4 branches on my tree. Why do I have 4 options and he says they're 3? Okay, so he's counting 2 branches like they're one single outcome. Agreed? And what 2 branches are those, Mackenzie?
The boy and the girl and the girl.
He's counting these 2 branches as though they're the same outcome. Now, they're different outcomes. Even if they're twins, they're different outcomes, right? Somebody was born first, okay? So these are 2 different outcomes. Another way of describing it is that you could actually take a look at the probabilities of these happening from our tree. So there are 3 outcomes, but you could also say that there are 4 outcomes if you consider the order that the kids are born in. Y'all with me? So let's actually put those diagram pieces in where we have our probabilities along the diagram. So we got the 1/2 here, and then we have it up here, here, and here, right? It's all 1/2s. So let's multiply along every branch and write the probabilities at the end. What is the probability of having a boy and then a boy? Don't overthink this. It's 1 out of 4, right? There's 4 tree branches, and all the tree branches have these equally likelihood kind of things going on. I multiply 1/2, 1/2, I get 1/4. What is the probability of having boy and then girl? Yeah, it's 1/4 again. I'll write this one down one more time. And then probability of girl and then boy, 1/4. And probability of girl and then girl, 1/4. So let's go back to Joe's statement. Joe says there's only 3 outcomes, and he is right. He is, right? But why is the probability not 1/3?
Because one of the outcomes can be 2.
Okay, so let me take what you said, Wiley, and change it just a tiny bit. So Wiley said one of the outcomes can be 2. And I would say one of his outcomes that he's describing can be achieved in 2 ways, right? So like Mackenzie pointed out, the things that are purple are 2 different ways of having a girl and a boy, right? It's the order of when you have them. Now, if we wanted to find the probability of having a girl and a boy, like those two things added together, we would actually add these two together. That looks like multiplication. Let me take these two and put a plus sign like that. If I added 1/4 plus 1/4, I get 2/4 or 1/2. The probability of having one boy and one girl, one of each, right, is actually 1/2. But his contention was that this one up here for the boy would be 1/3, and it's 1/4. Because there's really 4 different ways of having the children because the order is part of what's happening here, right? So let's come up with something to actually say to Joe, because that's the question that's asked. Let me make this, or try anyway, to make this small enough that I've got space to write. Okay, that's not going to work. Let's go with that. It's tiny now, but we write it down already, right? Y'all are good. So we're talking to Joe, and you don't have to do it in this order, but I like to tell people what they did right first. I think it's a nice way to intro into telling them they're wrong in the end. You know, it's kind of nice. So, yes, there are only 3 outcomes. But one of those, which is a boy and a girl, can happen in 2 ways. So the probabilities of boy, girl, and girl are not equally likely. You guys remember answering questions about whether things were likely or more than likely or not likely, right? These are not equally likely at the very least. Okay, they're not equally likely because boy-girl happens as boy-girl or girl-boy, creating 4 outcomes. Okay, it creates a 4th, dynamic of whatever's going on here when we're looking at this counting. All right, are you ready for the next example? Because it's story time. Are you? Okay, this is real life. Huntington's disease. Has anybody heard of it? I've got a couple nods. Huntington's disease runs in my family. My grandmother had it, and so did my father. Let me talk a little bit about what Huntington's disease is, because I want you to experience sort of the magnitude of what this problem represents in my world. Huntington's disease affects your central nervous system, okay? So what it does is it keeps your brain from telling the other extremities of your body, all of them, how to work or when to work and do so in the right timing. So I have specific memories of my grandma being at a place like a Golden Corral and not being able to stop the ice cream dispenser in time, and there was ice cream everywhere, okay? I also remember being in the car with her when I was maybe about 10 years old, and she couldn't stop in time to avoid hitting somebody in front of her because her reflexes had slowed down. She eventually lost her license for good reasons, right? My father also had this, and the thing that eventually happened for my father was that he would try to maintain his balance because you're off kilter on your balance as well. And so at the time when my children were young enough that my father was still living, they would have described my father like this. He walks like this. He walks all hunched over because he could keep his balance better that way. What eventually happens is that Huntington starts shutting down symptoms or body parts enough that you can't swallow. So my grandmother couldn't swallow, and so that actually was sort of the ending of her existence, was about the ability not to be able to eat. And so it's really tragic. And when someone has it, you have a 50-50 chance of passing it along to another person, to your children, your biological children. So my grandma had it, which meant that my father and my aunt each had a 50-50 chance of getting it. My father did have it. My aunt didn't. Doesn't have to work that way, right? You don't have to have a boy and a girl. It didn't have to be that they both actually had it or didn't have it, but it also didn't have to be that it was one of each. My grandma also had this really weird thing where Huntington's disease is found on a specific chromosome, and it's triplet repeats that are counted, A's and G's and T's and P's, and I don't know how it all works because I'm not a biology person. Probably can go talk to Dr. Marsh, the male. He could probably tell you. But on this chromosome, one of the two things you're going to get from mom, and one of the two numbers of triplet repeats you're going to get from your dad. So with my grandma, she had the gene that had Huntington's, right? Because she had the higher count. But her other count was also high enough that it was in this sort of gray area, which meant that if you got that count, which is my aunt got, she wouldn't have Huntington's, but she had the ability that it would increase if she had children. So her children could still end up having it even though she didn't. In my dad's case, we had a 50-50 shot because he got the one that for sure it was a 44. My aunt's was a 34, the triplet repeat count numbers. And so in 2001, I was, how old was I? 22, something like that, 21, 22 years old. My parents decided to tell us that this is what grandma had. We didn't know what it was. We knew she wasn't well, but nobody had ever told us what she had. And they told us at Thanksgiving. My husband and I were living in Kansas at the time I was married. I got married really young. We were living in Kansas. We were home for Thanksgiving. And so they told us, I was married. I'd been married for several years, so I guess I was 22. My sister was married. She'd been married for almost a year. My brother was seriously dating the woman he ended up marrying later as well. So all three of us were there. They tell us this is what grandma has. And they tell us not only is this what grandma had, because she'd already passed away at that, no, she hadn't passed away at that point. This is what grandma had, but also my dad had been tested, and this is what he had. And so I did this problem, but not with trees. I did it with the numbers in my head that night in our room, processing through what it would look like if we had biological children. I'm the oldest, so this branch is me. There's two outcomes. I either have it or I don't, right? And because of the way genetics works with this particular disease, I either have it from my dad or I don't, and it's equally likely, which means each of these branches has 1/2. Let's do it in decimals. We haven't done as many of those. My sister is the youngest, not the youngest, the second is what I meant to say, the second. And she's got these branches, and the same is true for her. She either has it or she doesn't. And all the probabilities, again, are 0.5. My brother is the youngest, so he's these last set of branches. And I'll abbreviate with H and D at this point now, if you're okay with that, just so I don't have to write quite as much. He either has it or he doesn't. So the first question that's asked, please don't turn your page, hold tight for a second, okay? The first question that's asked is, what is the probability that at least one of us has this disease? We've looked at a problem like this before. If I wanted to find that, I'd actually have to find quite a few branches. Every branch that has the word have on it, I'd have to find all of them. And then much like our example over here with Joe, I'd have to add all of those branches at the end together. But the reality is there's an easier way to do that, and it was the complements principle that we looked at a couple sections, or last section in 14.1. This branch down here at the bottom, that's all don'ts. That's the only one that puts my family in the clear, right? So this is the math that I did that night. I multiplied these three things together. Again, don't turn the page just a second. Grab a calculator, and I'd like for you to multiply 0.5 times 0.5 times 0.5. And we'll just write it over here to the side. 0.125. So this is the probability, 12.5%, right? That's what that represents, that we are all okay. How would I find the probability that at least one of us has it?
Subtract 1.
Yeah.
Or write that from.
So I'd either subtract this from 1, or if I were thinking percentages, I would subtract the percentage from 100. So if I take 1 minus the 0.125, what will I get? 0.875. So my parents had 3 kids, and there's an 88% chance that at least one of their children are going to suffer with my debt. So my husband and I made a decision that night, thinking about the mathematics of this, not the tree itself, but the mathematics of this, that if I had Huntington's disease, we weren't having kids. And that was not a popular decision that we came to. My mom kept looking back and saying, but if we had done that, then we wouldn't have had you 3 kids. That's true. It's absolutely true. The reason that they told us at this point as opposed to earlier is because of genetic in vitro fertilization, where you can create the embryo, and once they're 8 cells big, you can test them to see if they have Huntington's. You would destroy the ones that do, and you would only implant the ones that don't. And in that circumstance, my husband and I said, that's playing God, and we're not doing that. We're just not. So 2 years later, it's in 2023 or 2003, and it was actually it was the beginning of the year, it was in August, I started the process to get tested for Huntington's disease. And we got the results back, oddly enough, when we were back home again on Thanksgiving break. And I don't have Huntington's disease. So we did this one. You can flip your page now. This is 0.875. I do not have Huntington's disease. Obviously, my family was very pleased at that point that I'd been tested and that I knew and that I was in the clear, and that was all good news. But God really worked in the lives of my husband and I during that 2 years, to the point that we knew that no matter what happened with that test, that we were called to adopt. That wasn't a popular decision at the time with my family either, because their statement was, well, that child could have a disease as well. So it's true, but that child's already alive. I'm choosing not to create one instead. It's the difference. And so those are the decisions that my husband and I made. Because I don't have Huntington's disease is why I have a biological daughter, Abby. That's why I have her. But because of those 2 years and this process that we went through is the reason that I have my other kids. That's it. That's the reason. And I have to believe that my father's looking down. And he's pretty happy with my family. I know I am. Unless you think it's all roses to adopt, you need to be called to do it. Because it's not. It's really hard. And there are times when you think, did we make the right decision in doing this? But we know we did, because it's what God called us to do. And aside to this, because I want to share it with you, we adopted Eli first. As we mentioned, he was a baby. And then we adopted our 2 older Ethiopian children after that. In 2017, I think it was 2017, we weren't trying, and I accidentally got pregnant. I'll say accidentally, whatever you want to use, right? Got pregnant. And I miscarried. And that was really hard. 20% of pregnancies end in miscarriage. That's not right number. 20% of women will have a miscarriage is the right statistic. Let me say it right. So in this classroom, that's probably about 3 or 4 of you guys. Right, statistics. Maybe none of you, maybe more. We had 4 kids at the time, and we thought we were done, and had our plates full, and we decided to sort of table that discussion and come back to it later. And because we came back to that discussion later from having, again, a really tragic experience in our lives, is the reason that we moved on to adopt through foster care and have Cam and Jewel, and then continue on to adopt Bouze, and we've got our son that's still stuck over there too. He's still ours. What Satan would use for evil, God can use for good. About a year ago, when I was teaching this, I was able to tell my students that my brother was having some brain issues. And because of the brain issues that he was having, they decided to go ahead and test him for Huntington's disease as well. So what is the probability that at least one of my siblings has Huntington's disease? So this is my sister, and this is my brother, which is unfortunately drawn in a bad order because we still don't have any results for my sister because she's never been tested. I won't draw the whole thing again. But we can do the same calculation along the bottom that we did before, but there's only 2 branches. So if we take 0.5 and 0.5, we get 0.25. And the probability that at least one of them has it then would still be 0.75. Still 75% chance that somebody in my family has it from my brother or my sister. Shortly after I taught this lesson last fall, my brother's results came back and he's clear. He has 2 children. They didn't decide to do what we did, and neither did my sister. They all have biological children. So the branch that exists right now isn't a branch at all. It's just, I didn't mean to circle that. It's just this. It's my sister, and we don't know. She has 3 children. One of her children has a baby. She was born Kimber. Kimber was born a week ago. And her son and her daughter, who are younger than that son, are also seriously dating people that they're probably going to marry to as well. And we don't know. We don't know about any of them because we don't know about my sister. At one point she was going to be tested, but then she found out she was pregnant. I think this is really interesting. Our medical community, they're all for abortion. They have no problem with it. Not all our medical community, I don't mean it that way. But the prevalent attitude among many is that it's not that big a deal. And oddly enough, Huntington's is something that they will test. Well, it's not oddly, I guess it makes sense, is what I meant to say. Huntington's is something that they would have tested on my sister and on my nephew when she was pregnant with my nephew. But once she has the baby, you can't test that child until they're 18, and they have to make the choice themselves. It's not doable. I mean, I suppose somebody did it probably somewhere along the way, but that's the way it's supposed to work. And so, since my sister had no intention of having an abortion, she was going to have her son, and she had no intention of testing him to know that about him from birth, she decided not to get tested at all. And so we're still at the point where we don't know. Do you remember when we talked about normal curves and standard deviations? It's on the test redos that you guys are doing right now, right? Huntington's disease, the average age of onset is the onset of your parent. So my dad's onset of Huntington's disease was in his 50s. This has a standard deviation of 18 years. Okay, so remember your bell curves. 18 years younger and 18 years older. That's a wide span. So if my dad was 50, it means it would go all the way down to 22 and all the way, is that right? Yeah, and all the way up to 68. So your average age of onset for 70%, 68% of the population would be in that huge span, which means you really don't know. So my sister's 45. She's not far away from my dad's average age of onset, but the fact that she shows those symptoms now doesn't mean anything. It doesn't mean anything at all.